Thanks for the brief introduction. Yeah, rather I start my presentation because I was not known what I need to be presented here. So I put all my slides over through, but I will skip wherever it's necessary or wherever it's not necessary. I will try to make sure that you get something from my presentation. Otherwise, people might be knowing that my name is too long, but people call me Siva. Most of my colleagues who are there, they also know me, but maybe seeing here now. Okay, what you see here, I'm not going to present everything what we do there in South Africa, but I try to optimize my presentations, what we've been developed, the Lidars systems in South Africa. So that's what my focus of this presentation would be here. So let me move on it. Yeah, as I told you that or introduced myself, it has been the atmospheric research group, which we have been built it in University of Kwazulu Natal in the discipline of physics. It's a department of physics in the School of Chemistry and Physics. So this just to indicate that you have a temperature profile of the atmosphere, the density and the pressure, which is exponentially falling. Then you have a different regions of the atmosphere. This is to illustrate what we do in the atmospheric research group from the ground to the ionosphere. Again, I just shortly introduced where we are and what we are from and what we are doing, just for the audience or the people who don't know where is the location where I'm coming from or where I'm working now. Okay, so most of you know that the Africa, we are at the top, at the bottom of the tip point. So that is South Africa. So that's where here. We have three major the capital cities, which will be Pretoria, Johannesburg. Then we have Cape Town and Durban. So we are located in Durban here. That's where the University of Kwazulu Natal is operating. So we have 5 different campuses. So we are in the Westville campus. So it's before it was used to be called as University of Natal, which has been built by Indian people for Indian people. But now the government has taken over. That's why the name has been changed into University of Kwazulu Natal. So our building is here, School of Chemistry and Physics. I just want to show you this building. You will see in the light with the laser later on the background of the building. Okay, that's my group. I just skip all those things. So you already have received the informations. What is the importance of the boundary layer and the lower part of the atmosphere, which has been important to the people and the living beings. So I skip here. Yeah, so what I do here, I just to introduce you what is the remote sensing here before I go into the radar. I'm not sure. I have not seen maybe the introduction on that. Some people might be curious to see. So you people know what is remote, because the remote we have been using for many of the day-to-day life, which you use for watching the televisions, where you try to operate your televisions to change your channel or to change the volume or to do anything in distance. Basically, you are lazy or you don't want to go to the televisions and then change the mode of operations. So you are controlling the device in distance. So that's what the remote is functioning for you. The same applies if you have the car where you try to unlock or lock your car with the remote. So we have a large number of remote devices which has been played, but the basic subject or the basic understanding what you have here, you are trying to operate something in distance. That is the meaning of the remote, which I want to inform you. Once you know the remote, what we have, even in your body, we have eye, which is nothing but a kind of a remote sensing instrument, because you are visualizing something without disturbing the object. So your eye is nothing but one of your remote sensing instrument, but you know that it does until 60 frames per second. But if you want to visualize something, some object, something to be hidden here, I'm not sure how many of you are familiar with it. South Africa has familiar to the game reserves, where you can able to see the animals in front of you. So if you are able to going there, and you will have some accommodation like this. And if you want to see some animal over hiding there in that place, so what you required is basically, of course, your eye has to be perfect to visualize anything, but besides that, you need the light to visualize the object. That's obvious. So if you want to have it in the daytime, you want to see what is hiding here. and you may have the sunlight, and then you can able to visualize there is a tiger behind you. But during the night time, if you take it, visualize the same object, you may not have the sunlight, or we say that the moonlight is not also visible for in that location. Then you need to use something, a device, which is nothing but a torchlight, where you will focus your torchlight towards the object and then you visualize. So that's nothing but active. So what you infer from here, the passive remote sensing, which is nothing but where you don't have a control on the energy source or the device what you are using it to visualize something. Whereas the active one, you have a control on the source what you are trying to use, means you can try to switch it on or try to switch it off, or the energy source has been included into it. So then it is called active remote sensing. So otherwise, the remote sensing can be defined as this way. It's a science on art, information, object, area, or phenomena, but the basic wording is not in contact. So that's, you need to be remember that. So otherwise, any remote sensing instrument you take, you have a different resolution which you play. That was the most important to identify or to what you required or what you need for your purpose. So this has been covered many of my colleagues and my friends. So you might have noticed the spatial resolutions. That means how closer you would like to visualize your atmosphere or the environment. So you might be using a Google map nowadays even to visualize the locations. So, and then you have the spectral resolution. That means how you can able to distinguish the wavelength or the frequency of what is being backscattered. So that can be defined. So the instrument will be vary with respect to that. Of course, the temporal resolution is also important for some cases where you need to monitor the atmosphere or the environment more frequently. In that case, you need to identify how frequent you require the measurements to be taken, whether the instrument is capable of doing it. Then the last one, which is not most important, but you also use the radiometric kind of to identify a right remote sensing instrument. So the reason why I'm saying that the Lidar is one of the active remote sensing. That's the reason I will cover it. So these are my team, what we've been focusing on. I will skip all these slides. So we quietly have some ground-based measurements. Then we also have large number of satellite measurements, which we will be using it mostly for our atmospheric studies. These are the few satellites which has been used. Otherwise, I covered this part, as I told you, the active remote sensing where the energy sources include, the passive remote sensing where it has not been included. So you don't have a control on the energy source what you will be using. So you will be using some natural resources to activate your instrument to work on it. So if you look at here, you have a radar and Lidar. That's what we are covering here. So the Lidar is nothing but one of the active remote sensing device. So people might be curious to see these two pictures, which I have taken in the same place, almost in the same time, but in the different day. So what you see here on the 19th of September, where you have a large number of scattering which has happened due to the sunlight, and you have the particles and molecules over that place there. Whereas on 21st of September, it's become clean. It's also due to the reason we had a heavy rain on the day after, and it's washed away the large number of the chemicals or the pollutions over there. So one of the advantage, what you take some photograph, when you take the photograph, you may have a very good, beautiful nature of the light, but in the background, you have a scattering of the light from the particles or the molecules, or it could be even the aerosols. So that could be even caused by pollutants. So you need to be addressed in that region as well. So instead of, as I mean to say, to take a beautiful picture is important, and the other way, we also need to take care of the atmosphere, which has not been polluted more. So it's basically the scattering of the light. Again, I don't take much time to introduce the Lidar. It has been done already. So otherwise here to highlight you, so we will be using a laser as a light source in comparison to the radar, where the radio signal has been used as a source. Otherwise, the basic principle is almost similar to the radar. So what is the advantage of using Lidar is nothing but, since we are using laser as a light source, So you will be able to get the scattering of the particulates or the target what we are looking, even from a smaller size compared to the radar. So the radars may be visualized in the size of meters, whereas the LiDAR, since you use a laser light, we can go around in the micrometer range to nanometers. So that's the advantage of using the light as a source in the detection and ranging. I will skip the remaining part because this has been already introduced by Professor Jayaraman and also my friends. So I will skip here. All right, otherwise to inform you again, this to say the LiDAR can be configured in two types. One could be the monostatic or bistatic. The monostatic, which we say that the transmitter and receivers are co-located, whereas the bistatic, which can be separated by some distance. Again, it has some advantage and it has some disadvantage. Of course, it also depends on the user requirements, what you want to use it for. If you are interested on the lower part of the atmosphere, then you need to have the monostatic mostly. And if you're not interested in the lower part of the atmosphere and where you've been burdened with a large number of particulate scattering, and then you may be filling your telescope and the photomultiplier tube. To avoid that, you may have the bistatic operations where you can focus the higher region of the atmosphere. It can be dependent on the region what you look like. And then it can be separated, the transmitter and receiver, by the distance. Again, I skipped this one. This has been already covered again. So these are the LiDAR equations. Yeah. This also has been introduced by Dr. Raghunath from NRL. Just to infer you that these are the physical process which you do, and the name or the device what is being called depends on the physical process used is been given here, and then the purpose of the what has been used to measure the LiDAR. So what you see here, a single instrument or the single term what you've been using depends on the purpose. It can cover the whole range of the steady in the atmosphere. So that's what it means. Otherwise, if you look at it, the LiDAR has been in different platforms, which can be ground-based, where you can operate it in a single place for a large number of time, whereas it can be having the mobile system, which my friend Virabhadran has introduced to you. So where we can have the system in the vehicle, where you can move and then make a measurements in a particular place you would like. It could be having the airborne, where you can not able to access through the roadways, but you can able to fly over there and then you can get the informations. It could be like a dense forest if you wish. And then we don't know if you need to have a global informations which can be observed through the satellite. Again, it has been covered in we were invited talk in the beginning of the presentation. So these are what we see in the ground, in the atmosphere and the earth, but there is also the LiDAR which has been mounted in Mars to study the dust in the Mars, but it's still going on. The study is still underway. Okay, otherwise, what I'm coming to my subject. So since left to Africa, we need to focus something to address why we need the LiDAR in the place. So this is the map which I have created like more than 10, 15 years ago. So don't worry if you don't see your LiDAR here. The star mark indicates where are the LiDARs located around the world. But you see in the African region, we don't have many LiDARs except those two. The one I developed in Pretoria, and then the one we have it in Durban. So there is another one, which is I'm currently here in Reunion, which is a French island next to Mauritius. So we try to make some network of the LiDARs. So that's where we are part of the triangular here. So if you notice that in South African region, the LiDAR has become, again, it's a new in kind to develop. As I told you, this is not the map has been made now. This is 15 years ago when I was working in CSIR. Okay, so otherwise why we do all these things? It's basic, the reason is our government is little bit tricky, not compared to India or any other countries. We have some preferred codes in South Africa. So what we use is pay as you earn. So that means you pay the tax, whatever you earn. It doesn't have any exclusions to do. And then you need to bring the money before you take the money. That means you get your salary if you bring your money. That means you need to focus your study, depends on the need. And we used to say nothing is for free. So based on these three quotes, you might be noticed here, though we do the research for enhance the science and the advancement, but we need to focus our research, what is need for the public and need for the government or for the nations. So in that way, we need to focus our studies towards in that directions there. So these are some of my presentation just to motivate myself. So if you are a researcher or scientist, you will be looking at where do you find your science, what do you want to do, how you want to do, and when do you like to do. But if you are the customer, if you want to get your customer, and then they expect from you why you need to do, what you like to do, and then how long does it take, and then how much does it cost. So I'm just putting some few questions across there. So you need to manage both from the researcher or scientist or from yourself to the end users, how you tackle them and then how you solve their problems. So that is the reason that why we need to build the LiDAR in South Africa to serve the community basically. So it's a mutual concept and then mutual interaction need to be undertaken from that. Yeah, so this is the first LiDAR system which I developed in CSIR for the atmospheric remote sensing. So it's on the vehicle basically. So we started from here, the vehicle with, or I started from here in this stage. So then we have completed the system with the different lasers and the scanners and the part of it for addressing different kind of pollutions and for the atmospheric gas scattering as well. So the system look like now in this way because we simplified the systems and then we also expanded the systems later on using Alexandrite lasers and CO2 lasers. I think Dr. Veeraputra has already informed you. So we are interested on the wide range of pollutant measurements, also the volatile organic compounds measurements using the tunable lasers and using again different detections, UV detection, the infrared detections for detecting the pollutants and the chemical volatile components. So otherwise the system look like, so again, I don't want to go more in details. So you will have a transmission section and the receiving section and the data acquisition system. So it depends on your need. This all need to be changed. It will be very, depends on your requirement, of course. Okay, otherwise, if you use a green laser beam, so we need to advise our civil aviations to just to threaten them or to inform them that they need to be scared when they see the green laser which is moving upwards. So we take the permissions so that it's safe and then we operate. Otherwise, as I said, if you're not operating at 532 nanometers, if it's not, again, optically dense, you may not need to take any permissions. And mostly the infrared lasers are eye safe, so which does not require any permissions with the airspace. Okay, this is a system when we have operated in our laboratory environment, and thereafter we moved the system to make measurements outside. So this is just to introduce the signal to noise performance. The noise is given in the red color and the signal is given in the blue color. So how we determined, we just to switch off the laser, but the detection system was on. So that's what you can see, the background light, what we have captured here on the right-hand side. Whereas on the left-hand side, we have the laser is on, and you also have the background. So if I subtract the background one with this one, then I get actual signal what I received from the laser which has been emitted. So that's how we determine the signal. And of course, these are the different products of the laser. So again, you can be able to see the cloud movements and the cloud structures over that height region. So that was the part of my work which I have developed at CSIR. So the system is now currently moved into the another place, which was developed in Pretoria first. And now it is been moved into the Richards Bay, where we are expecting large number of sugarcane burning, which we normally call as a biomass burning. So we would like to study the biomass burning aerosol transport. So that's why the system has been moved to that location for continuous operational now. So I also moved from the CSIR after my 5 years of work environment there. I currently working at the University of Kwazulu Natal in Durban. So where we have Relay and me, Raman Lidar. It's almost similar to what we had in previously at NRL, where I was working for my PhD during that time. It's almost a similar LiDAR kind. it was there, but we have been relocated from one campus to another campus, and then the system was not operational during that time. So what I need to do, my job was to refurbish the whole system to get into there. So if you look at now, this was the old system which was in the track in the container, and then we moved down to the other campus where I told you, in the Westville campus, and then we operating here now in the chemistry and physics, in the physics discipline, and you can see the laser beam and the background light of the Westville. The system look like that. We will be having a NDR lasers, which has been operating at 532 nanometers, which is nothing but the second harmonic of the laser. And then we will be detecting three different telescopes. Two will be measuring for the molecular scattering for the Rayleigh part, so that we can able to measure the temperature. And then the smaller telescope, which has been used for the aerosols. It's almost as similar to what has been classically used in NRL as well. But as I told you that the system was very old. It has been measuring from 1985. The system was operational from there. But the time when I have joined, like more than 10 to 12 years ago, nothing was working perfectly. As I also told you that we have moved everything from one campus to another campus. Then I diagnosed the situation. So where you see all the red circle, that's where the problem have been noticed. So then we need to refurbish the whole system to make it operational again. So what we did, we tried to change whatever, how it depends on the funding availability. So we changed the lasers. You can see the empty, and then here you can notice, if you see the advancement in the technology, if you don't know how big will be the old PMTs. So these are the old PMTs, which does require the cooling part. So we are using the water to be circulated in the background to get cool the PMTs. But nowadays the new PMT doesn't require the cooling sources. It can operate at the room temperature. So you can see that the size and everything has been reduced as well. So you can see again the data acquisition, which is quite long and has been reduced into smaller size nowadays. Of course, the PC and everything. So we changed almost everything. So these are the changes has been made. Then we have made it operational again, the system, and the system has been operating again from 2015. We are continuously observing the atmosphere. So this is one of the results which we got it from the Durban Lidar. That's a fixed Lidar I said before. It's in the room, and this is in the outside. How does it look? Then again, you know that when you have a system, you need to calibrate the system. So what we did, that we brought the old system from CSIR. We parked next to our campus, and then we operated together. So we have the same green laser, which has been emitted from the mobile radar, and then we have a fixed radar on the other side, and then we calibrated the system 1-to-1. Of course, we also have the other radar. I will talk about it in just the next few slides later. Yeah, so these are the distance between the two radars, which has been, or three radars, which has been located coherently in the same campus. It's about 167 meters. So this is where the fixed radar is located, and then the other side where you have the mobile radar and the portable radar was been located and operated. You can see the two laser beams which is moving in the same locations, which could able to get. So these are some of the return signals, and this is from my team. Yeah, so in that way we have calibrated the system. But you know that what we have been operating so far is the radar is vertically moving upwards. But you know that the stack, the chemical pollutants, which does not move vertically upward direction, it can go towards any direction of the wind. So that we need to be tackled, or we need to identify how much it can be dispersed and what will be the distance it can be moving along, and then whether it could be harmful for the living beings or anything which has to be addressed. So in that way, the vertical measurements may not be helpful, because if you measure the vertical measurements in a particular place in a particular way, it may not helpful if you are looking at the pollutants which is moving with respect to the wind speed and wind directions in the particular direction. So you need to have the radar which can be scanning around the system, and then you can able to monitor So then we have hired the ray matrix. We got almost all the what you call the equipments and everything there. Then we assembled it to get the portable radar. So this is a 2-dimensional scanning radar, which we use for aerosols, cloud and water vapor and temperature measurements up to 40 kilometers, depends on the, of course, the laser signal. If you have the signal is too high, powerful, then we can able to measure until 240 kilometers there. So what is that it does? So these are the, again, the major characteristics of the lasers. So we have a transmitter port, the receiving port, signal and data processing, and then the PC over. But what I will do that, I will just cover what are the basic characteristics we have used. So we have using NDIAG quantum lasers, 355 nanometers. This is the third harmonic of the NDIAG. Because you notice that the second harmonic is of 532, the third harmonic will be approximately 355 nanometers. So again, those are the beam characteristics which has been emitting. The advantage what we have here, we just use normal webcam over here to identify the locations where we are pointing the lasers, so that we could be able to see the target visualized by the picture, and then we can also get the measurements done using LiDAR at the same time. All right, I will skip all those part. If you are interested, we can have more in details. I think I gave some presentation of the materials to Dr. Raman, so maybe he will share you that lecture notes for you. So I will skip again because this is also been covered in the morning, how the telescope and how does it look. These are the different PMTs, the output which we will receive. Here S and P stand for parallel and perpendicular component, if you are interested to look at the depolarization characteristics of the scatterers. Okay, again, I skip those parts. These are, yeah, so I come to here. So what we have designed here is nothing but the portable, as I said, it could be movable in 2-dimensional, either in the horizontal direction or the vertical directions. What we have used is a simple concept of the solar radiometer. So maybe you may be familiar with it. The solar radiometer measures the radiation from the sun. It focuses the sun with respect to that the movement. So it's geoly coordinated, and then it may have that calculations internally to identify the location of the sun. We use the same concept here. We moved this part into here. Basically, you can see exactly the same what we have here. It's been adopted here in the portable scanning radar. So what it does, we can able to focus into a particular locations, and then we can also move the system accordingly, and it can be controlled via GPS, so that we can also identify exact location geographically. So that's a vertical cabinet. These are some vertical measurements which we have been used in the using the portable radar. And these are the different scans which we done in the azimuthal directions with respect to different angles, which you can able to see. Then we can also do on the vertical scan. You can also able to see here in the y-axis in the north, different angles which has been moved towards the east directions as well. Otherwise, one can able to visualize the signal like this way. When we are moving with respect to the time, and then the locations, if the pollution is moving in particular directions, we can able to easily visualize from this portable, the scanning radar. Depends on the requirement, depends on the directions where it is moving. So this is to give you, again, zenith direction. So you can vertically or horizontally, you can slice up the atmosphere, and then you can able to visualize the information from there. You can also be able to present the map, your presentation of your how the pollutant is moving. You can present it even in the Google map. As I told you, it's a GPS inbuilt in there, so we can be able to get the geolocations accordingly there, and then you can represent in the Google map. Okay, so these are the calibration. We did all the 3 lidars together, which I have already informed you the locations. So where you can able to monitor everything almost the same. As I told you, the lidar stand for detection and ranging. So where you need to identify the exact locations, which has almost been identified by all the 3 lidars. Of course, you might see the different features will be vary because it could be difference in the specifications of the radar. It includes the telescope configurations, the laser transmissions, the energy source, and the different parameters which has been used in it. So that could be some changes there. But otherwise, the basic principle to detect the range has been identified exactly the same for all the 3 lidars together. Otherwise, the lidar can also measure for the pollutants, which already has Dr. Veeraputran has covered, where we use the signal on and off wavelength. That's what we used for detecting the volatile organic compounds, and then some of the chemicals, pollutants, including sulfur dioxide and methane, which have been used largely. We also used for the smoke detections for the radar to identify how far the smoke can move or the fire can be dispersed. I will show you another slide where we are building another radar for the fire detections in later on. And then you know that for the cost wise, it's very high. I'm not sure how many of you know that the basic, the laser is very biggest part of the money which goes into there. If you want to reduce the cost, and then you need to optimize your studies. So this is the one which we are trying to build is a LED mini radar. So we're using LED as a laser source to have detect the ocean waves to basically to identify the tides, how big the tides, whether it is harmful or not, we could be able to detect it. And then this we are trying to use it in the harbor in the urban region as well. So this is in underway to build it up. And also we are trying to build another radar for astronomical and atmospheric studies. So we are trying to use our portable radar, and at the same time we want to use the astronomical telescope to visualize the astronomical signal. I'm not sure you may be aware of that because the astronomy and the atmosphere, they are against each other, because they like normally the what you call the clean, where you want to get the stars and the light and everything from the sky. But we don't want that light, because we'd like to have the light emitted from the laser and which is backscattered back. So we don't like the background light anyhow. But if you have co-located in the place, then if you could be able to have break your signal into 2 parts, some part of the signal to go into the laser and then identify what is the atmospheric transmittivity, and then you can be able to correct the atmospheric transmittivity in the astronomical images that includes the stars and telescope, what you will be able to visualize in the stellar object, which can be able to identify and correct your image from the atmospheric corrections. So that is the objective of that. We're trying to co-locate in the 2 places, 2 lidars, and then to identify that. So this is also undergoing in the subject. Besides that, we are in collaboration with Algeria, where we are trying to develop the atmospheric radar, mainly for 2 purposes. The one is for the forest fire detection. So the Algeria has a large number of forest fire. So this could be natural causes mostly by the methane emissions over the place. So we need to detect the forest fire and then give like a warning signal for the people. So this was been identified, and then we'll be using here mobile radar system to using 1.57 micron. It's in the infrared region, of course. And then we're trying to mount it on the mobile system to use it. But in the same time, we want to change only few, the lasers and the few of the optical detecting part, and then use it for the atmospheric studies. So this will be look like same the radar, but changing the lasers and some detection system, we could be able to use it for the atmospheric studies. Again, this is also in underway for the study has to be concluded in very future, maybe in a month or maybe around by end of the year, because we have been stopped by the COVID for last 2 years. We didn't have much development there. Yeah, with that, I would like to thank my collaborators. These are my national or local collaborators in South Africa, and there are some international collaborators. I have not included here European Union, so I would like to thank European Union as well. That's a part of that why I am here now at Reunion. Okay, I included here is Erasmus here. Okay. So these are my funding agency, of course. With that, I will stop here for questions. I also expect if you are anybody interested for having master's or PhD, or mostly I'm looking for postdoctoral, if you are interested on the radar work, to work on the portable radar or fixed radar or the astronomical radar or the mini radar, you are most welcome to contact me. Thank you.